compensation. So now let's say we have this cap which is C. We apply a V in voltage. So what is current? I in V in times CS. Now if I want to increase this current. So let's say IN, I want to make it, or I would call it K times IN. Then two possibilities. Number one, increase C to K times C. Okay, and second possibility is increase V in. So increasing V in is not feasible, obviously, because if let's say you have a 1 volt and you want 10 times capacitor, you have to put a 10 volt, and 10 volt may not be basically, it will be what I say, you may have some reliability concerns. Obviously your devices will blow off at 10 volt also, because these devices are supposed to be operating at 1.8 volt also. Okay, and if you have a small signal, you are looking at a millivolt and increasing it to 10 times, then it might be possible, but then you need amplifier and all those. So alternate way is, if I change the ground, let's say, instead of having the ground at a fixed 0 volt, so in order to change the V in, ultimately I want to change the voltage across the capacitor. Okay, so either I fix the ground and change the V in input voltage, or change the ground voltage. So if I do this, this is your C and this is your V in, and if I make it minus K minus 1 V. So what is the voltage across the cap? What is this voltage? V in minus K times V in, sorry, KV na, minus V. So now you will get K times V. So which means this is your gain factor, correct? So can I do this? This is equivalent to putting an amplifier with a gain of what? Minus K minus 1 V C. And can I represent it like this? Sorry, K times C. Okay, so which means if you put the capacitor around an amplifier, the negative feedback, the capacitor looking at the input will be multiplied by the 1 plus gain times. Okay, and if gain is very large, more than 100 or so, you can approximate, say, gain times. That's what is called Miller effect. So now you have this amplifier. Okay, this is your Vin. What is the output?
Output is minus K.
GM
Minus GM.
R out, okay, multiplied by V. So now if I put the capacitor around this, I will call it CC. What would happen? What will be the capacitor looking at the input? Can I represent this as so I'm not right now I'm not ignoring the effect at the output cap, but we'll take into the effect when we do the actual analysis, but I'm just looking at the input cap. What will happen here? So what is the cap, this cap value now?
This cap value should be 5 nano.
GM
GM
R out multiplied by
CC.
CC. Okay, and if GMR out is, let's say, I mean 20, 10 or so, I mean usually you have more than 50 or so. So now assume, let's say this guy is how much the gain we got last time?
300.
300. So now divide your 5 nano with 300.
16 picofarad.
Okay, so that is the capacitor you will require now. Now which is feasible to implement on chip. Correct? So if GMR out is large, then CC is quite small. So assume previous case CC required was how much? 5 nanofarad. GMR out was 300. 300, huh?
300.
So, and CC actually now CC plus CO1, okay, is divided by 300.
Uh, 16 picos.
16.6 and which means CC is minus 6.4 we had, so which makes 10.2 picofarad. 10.2 picofarad is very small. Huh? So one thing you need to remember, when you, now this capacitor is a function of your gain, and the gain, output stage gain is changing with the load current. Okay, so you have to make sure that at the maximum load current, this obviously this will move, this capacitor will get smaller, huh? Which means your omega P2 will move at a higher frequency, but at the same time your output pole is also moving at the higher frequency. So if both are tracking well, then your phase margin will not degrade, but your bandwidth will be increasing actually. So that will not hurt, it will further improve your transient response and all those. So all you have to just make sure at a max load and min load, there is no case where your output pole becomes closer to your UGP. That's it. That's all you have to ensure. So based on that, you may have to slightly increase this capacitor or overcompensate it, so that at higher load current, you get a good phase margin. That's it. So when you start considering at the output stage this effect of this cap, it will cause a pole splitting, and it will further move your output pole at higher frequency. So that's another advantage you get. And when your output pole is moving at higher frequency, now you have a freedom to move your dominant pole at higher frequency, okay, and build a higher bandwidth. And we have to consider right half plane 0 also here. So this capacitor will cause right half plane 0, which will degrade your stability, phase margin. So that also we need to consider, and how to get rid of that. Okay, so this should be CC actually. The reason is and from the previous stage you had RO2 and CO2. So after this Miller compensation, what should be this cap? GMR out. So CC. Correct. So GM R out CC is much larger than CO2, because now it's multiplied by, and you know that this order of picofarad, and so multiplied by the gain, so it will look much larger than your 6.4 picofarad cap. So it should be CC only, not CC plus CO2. So your CC will remain this. Okay. So let's look into right half plane 0. So if you consider this case and put your capacitor in the feedback CC. So from here it's very hard to determine that it's really have right half plane 0, because we are considering ideal amplifier. But when you change this to a real amplifier, which is nothing but your GMR out, and since we are interested in transfer function, so now just find V out by V in for this. So you have 3 currents, this, this and this. Just apply KCL at V out. So V out minus V in S of CC plus V out over R out equal to what? Minus V in GM. So V out S of CC minus V in so this can be written as V out equal to okay. Correct. So, what is this? This is your, so you have a 0 which is appearing at 1 over GM over CC, and this is right half plane 0. I am not interested in the pole because we have modified this transfer function. Actually, when you look at the previous stage, so here what you have, if you take from the previous stage, you will have a capacitor CO2 and you will have RO2 and you will have a current from the previous stage, which is will GM times V in. So, if you want to find the overall transfer function, you have to include all those, but just in order to show that there is a right half plane 0, I just simplified everything and only consider this CC, because if you consider all those caps, then it will complicate the things. So, there is a right half plane 0, and now if I do this, and you can do this at your end later. If I put a series resistor RC, then what will be the 0 location? Can anybody tell? This will be 1 over GM minus RC into CC. You can derive it, you will get that. So, now if RC is greater than 1 over GM, your 0 is in left half plane, correct? And if you make RC equal to 1 over GM, then where is the 0? Infinite. So, 0 will disappear. So, using this series resistor, you can either cancel the 0 by matching your GM with 1 over GM with RC, but usually it is very difficult to match them, because GM is coming from your MOSFET and resistor is a different component. So, difficult to match, but if you implement this R using MOSFET, then you can track them. Okay. Up to some extent you can track them, but it is very hard to perfectly cancel, that is what I am saying. Another thing you can do, now it is in the left half plane, you can overlap this with your non-dominant pole, the second pole. So, you can convert the second order system effectively into a first order system and extend your bandwidth, because now second pole is not into picture, only one pole, and first order, you know, the maximum phase shift can have 90 degree, so you can have much higher bandwidth. So that's another advantage of having this.